All right, guys, so we're going to start our afternoon session. David's going to be telling us, I guess, two problems. Two questions.
They're not, hopefully not problems. So I'm optimistic that someone here will be able to quickly solve these things. I think they're easy, or maybe not. I don't know. You guys can tell me at the end of this. If you look at my abstract, I was going to talk a little bit about this different style of randomized methods. So these are these old Monte Carlo methods that take a linear system and turn it into some random walk estimator. And we had some recent work on this, but I decided to talk about something different. And so if you cared about the first one and were really annoyed that I'm not doing it, well, there's an archive paper that describes everything I know about that one with all the bounds and yada, yada, yada. So I'm going to tell you about two problems. These are things where I don't know the answer. So the first one will take about 3 slides to get to the key question. The second one I'll give a little bit more background for. But anyway, again, I hope these are easy. So again, I don't have an answer to this. I'm not trying to be coy. If it's really easy, please tell me. That'd be great. So everyone, I think, has seen a slide something like this before. If you take a random Erdos-Renyi graph and you look at the eigenvalues of it, you get one of these semicircle laws. And so here what I'm doing is essentially I've got 3 different graphs. And I think these are 200 node graphs, and I'm varying the average degree from 10, 20 to 30, and I get eigenvalues of the normalized Laplacian. These things lie between 0 and 2, and there's some nice semicircle law that you can look up in the textbook, which will fit the eigenvalues or the distribution of eigenvalues of these things. So I'm plotting empirical distributions of eigenvalues like Michael did yesterday for those neural network weight things, except these are graphs now. And again, if you vary this, you can get sort of, so as we go from an average degree of 20 to an average degree of 30, yes, the distribution changes, but it changes in an expected way. So this is all well known, nothing new there. So recently we've been doing a little bit of work on what we had at the time called higher order data analysis, but it's really quite a simple idea. So we're given a graph here and some adjacency matrix A, and essentially what we're going to do is instead of working with the adjacency matrix A, we're going to work with this weighted matrix W is equal to A squared Hadamard A. What does this matrix do? Well, for each edge, so this is an element-wise product, this is going to count the number of triangles that utilize that edge. Where does this thing come up? Well, this arises from work when you try and generalize things like graph cuts and all sorts of other things to looking at them on tops of as instances of motifs. So you take a regular graph here, you enumerate all triangles, you sort of build a hypergraph of this based on those triangles, and then you say, let's look for small conductance partitions of this hypergraph. It turns out you can relate those back to this matrix here when the way you build the hypergraph is a triangle. And if you want to read about that, we have a whole sequence of papers about that. Okay, so then this begs the obvious question. What happens when you look at this matrix with that Erdos-Renyi construction and look at the eigenvalues of that at the normalized Laplacian of this guy? So what we're doing here is we're going to generate a random Erdos-Renyi graph. Again, we're looking at the same thing where the average degree is 10, 20, and 30. We're going to compute this weighted matrix. W is equal to A squared Hadamard A. Again, this is a symmetric matrix, so this is essentially counting the number of triangles incident on an edge. We're going to compute the eigenvalues of the normalized Laplacian of the largest component of A. It doesn't really matter if you take the largest component of A. It's just if you don't do that, you get a little spike at 0 here because these things can be disconnected. And then we're going to look at the distribution of these things. And so if you look at this for the 10, 10, 20, and 30, you get things that look very different. These are clearly not semicircle laws. If you stare at them long enough and you look at sort of distributions of random matrices, you would think, maybe this is a Marchenko-Pastur law. And so in the blue or in the purple curve here, I've done my best to fit a Marchenko-Pastur law to this data. And as you can see, so this is trying to fit it to the green curve, which is the densest one. I thought that would be the easiest one to fit. It doesn't actually fit to any of them as far as I can tell. But you know, like it gets the sort of, I don't know if you want to call this the head or the tail, but it gets this side right, and it doesn't do so well over on this side. And I spent some annoying amount of time playing around trying to get combinations of semicircle and Marchenko-Pastur and all sorts of other things to try and fit these things better, and I haven't had any luck. I've talked to some handful of people and showed them these pictures, and everyone sort of scratches their head and says, yeah, it's an interesting distribution. So the question is, what is this distribution? Can we characterize it? Again, I sort of hope this is an easy question. I think it's, yes?
Did you ask Joanna?
No, I have not asked Joanna yet. So is she here?
No, but I bet she could answer this question.
Okay, well, so now I have one more person to check. So in case you want to reproduce this, all the code is on this GitHub gist here. So if anyone has a phone and wants to like email her live or something, then maybe we could have an answer by the end of the talk. You know, again, it's just a few lines of code to reproduce these things. You know, it's possible it's some convolution of things. Why does this matter? Well, essentially, if you want to know why this matters, we actually get much better results on partitioning stochastic block models by doing this triangle pre-processing first. And so if you're doing any type of linear algebra model for partitioning these stochastic block models, I've got a whole other talk on sort of nice little things that you find when you look at identifying partitions of these stochastic block models, and these seem to be a lot more robust than just doing things based on the adjacency matrix. So the idea would be if we can characterize this, that might actually help us understand some slightly more robust things we can do on those ones. Okay, so that was the easy one. The next one is, so this is another problem where I don't know the answer, and this is going to involve correlation clustering of low-rank matrices. Again, if you can't stand suspense, this one, essentially all of what I'll talk about for the next little bit, except for the question, is on arXiv. So there's a paper we wrote about this that's on arXiv that talks about it. It doesn't actually pose this question. The question is just sort of left implicit in the paper. And so just to cut to the chase, one of the things we use here is a heuristic randomized algorithm for sampling vertices of zonotopes. We use this to approximately solve binary optimization problems, and we get really good results. And the question is sort of, can you say anything more rigorous about that than, hey, you get good results? So we find that empirically. Okay, quick show of hands, who's heard of the correlation clustering problem? Okay, so some people, but most or a lot of people haven't. So I'm going to give a quick introduction to it. There is extensive literature from a whole host of communities on this one. So if you have a question, it seems like I didn't answer it, there's probably a reference somewhere out there who, and or someone in the room who knows the answer. Correlation clustering is this nice formulation of the clustering problem where rather than given as input data points, what you're given as input are relationships between data points. And so this takes the form of a signed graph where a positive edge indicates that two data points are similar to each other and they should be in the same cluster, and a negative edge, which are drawn here with red dashed lines, indicate that two vertices want to be in distinct clusters. And so the nice thing about this is there's no specification in this problem of the number of clusters that you have. If the input graph or the input matrix, we'll see that this is really a matrix here in a second, is all positive, then that means that everyone wants to be in the same cluster, and so it's kind of like all your vertices having a big group hugged together. And if everything is negative, that means that everyone's going to be in their own individual cluster. These things can be weighted. In general, weighted problems are harder, so hopefully they're not. We're going to look at weighted cases. And there's two types of objectives that people look at here. The things that people look at are essentially minimizing the number of mistakes. So find me a clustering that makes as few mistakes as possible. Essentially if I cluster these three vertices here together, there's a negative edge included, and so I don't want to, that's one mistake, and then here's a positive edge that's between clusters, so that's a different mistake. And so I want to minimize the number of these things. If there are weights, I'm going to minimize the sum of weights on those edges as well. Another thing you could look at is maximizing the weight of agreement. So you either minimize the weight of mistakes or maximize the weight of agreements. From the perspective of integer optimization, they're nice and the same. From the perspective of approximations, they're not at all the same. So one is much easier than the other. But that's not what I'm going to consider here. What we're going to look at is essentially taking this and looking at these things as matrices. And then one of the great things about having matrices is matrices are sometimes low rank. And so the question is, what happens with low rank correlation clustering problems? So you might ask, is this just an artificial construction? No, there are actually problems in the literature where they legitimately have low rank correlation clustering problems. They're not all that common. But on the other hand, we can do some nice things with them. So if your matrix is rank 1, I think everyone in the room would be very happy to be given such a problem. This is a particularly nice correlation clustering problem to have. Essentially, what we do is we have a positive semi-definite matrix that's rank 1. If we just sort that vector v, we sort it into two groups, essentially vertices that have negative entries and positive entries. So again, what we're doing here is we're taking this matrix of weights here and assigning the weights corresponding to the vertex. So now the weight on your edge is the product of your things. And so again, essentially what you do is you get groups based on the sign of this thing. So you just look at the signs of these and you are happy. This is an optimal clustering. All right, some other fun things. Essentially, if you have a single, so if you take correlation clustering and take a sort of rank perspective on this, what you find is, first of all, if you have a single negative eigenvalue, that turns your problem into basically makes your problem NP hard. So even if you have a rank 1 negative definite matrix, that's not something that we know how to solve efficiently. So we're going to just look at the case where everything is nice and positive definite, in which case it turns out that a rank R positive definite matrix can be solved in polynomial time in order n to the r squared minus 1. So that's a lovely runtime. So I can solve that for about r is equal to 2. For r is equal to 3, that would be an n to the 8th algorithm, which is not something we're going to be able to do. Now, how do we...
Some exhaustive algorithm that you have?
Essentially, yes. So the algorithms are the simple one. Okay, so essentially the right way to think about this is it turns out that there's an equivalence between correlation clustering in the low rank sense and this problem called vector partitioning. And vector partitioning can be solved via essentially enumerating vertices of a Zonotope, which is where we're sort of going with this. And so if you just exhaustively explore all vertices of the Zonotope, you must look at the optimum clustering at some point. And so you just have to bound the number. I mean, it's essentially just a bound of the number of vertices of these things. Okay, so that's not something that's overly fun. It's based on some older work. But in some work we were doing about the same time as we were working on this one, we actually had looked at a particular randomized algorithm to sample vertices of the Zonotope. If you haven't heard what the Zonotope is, I'll go over that in a second. And so in practice, what we do is we find that this is a highly effective procedure. And to cut to the chase, the question is there anything we can say about this beyond that, hey, this seems to work in practice, but we can't say anything more? All right, so if you want to sort of see what the vector partitioning problem is, in this case we've got a cluster C, and what we're trying to do is maximize the norm squared of what are called sum points. So a sum point is just the sum of all the data points assigned to that cluster, and what we want to do is figure out a cluster that maximizes this norm here. The sum of this norm. It turns out it takes a few lines of algebra, but it's not particularly complicated to show that low rank correlation clustering in the positive semi-definite case corresponds to this. Yes?
Sorry, just before we move on from the last slide.
Yes.
Is when it's positive semi-definite, some of the negative eigenvalues, is it NP hard when it's rank n?
So when it's rank n, and sorry, so this is in general NP hard, but sorry, when it's positive semi-definite and rank n, and there's no negative eigenvalues.
Yeah. You don't know for this case.
That is a good question. I don't know off the top of my head if that case is, yeah. Great question.
So it could be even like not 2 to the r. It could be like poly.
It could, yeah. So, I mean, yeah. Okay, so what is a zonotope? Just another quick show of hands. Who's heard of a zonotope before? Okay, so fewer people than correlation clustering. I hadn't heard of these until someone asked me, what the heck happens when you take a hypercube, project it to a low-dimensional space, take a picture of it, and try and find the convex hull? So it takes a while, if someone describes things that way, to figure out that the thing they're talking about is a zonotope. There's some interesting story about how we realized that that was actually a zonotope. But essentially what we are given here is a D by N matrix. So think of D as smaller than N. And so N is going to be sort of some ambient space. And so G is going to take stuff from a high dimensional space down to a low dimensional space. We're going to look at a hypercube here, and we're going to take all vertices of that, project it down to our low dimensional space, and then find so a vertex of the zonotope is going to be essentially one of the vertices of the convex hull of that projection. Okay, so here's some cool stuff. So at that, or around that time, what we were looking at was the following randomized algorithm to get a vertex of the zonotope. You take a vector x that's just essentially randomly distributed according to a normal distribution. You multiply by G transpose. You take the sign of that, and then you multiply the sign of that output by G. You do have, there should be a star there which says that nothing can be 0 when you do this, but in the interest of keeping the slides nice, I'm going to omit that step. And now what I'm plotting here is for a 2 by 3 matrix G here. What we're seeing is over a whole bunch of samples how often you generate each vertex. And then here we have a 2 by 10. So essentially as we crank up the dimension of that latent, or of that bigger space there, first of all we get more vertices. So the circles here are the vertices. And now the question that we were trying to answer in some of our work was, what's the probability that we get an individual vertex? And so over here, you know, it looks like as I'm sort of throwing darts at this thing, you know, at every, yes?
Why are you guaranteed to get vertices? Don't you have things that's contained in the...
So it turns out, it says, yeah, this will always give you a vertex of a zonotope. So it will always give you one of them. There's a short derivation of this I just didn't put in here. But if you look at this, this will always get you one. It will actually, with non-zero probability, get you any. So there's a probability distribution that I'll give in a second that sort of says what the probability you get any particular one is. But again, for this one, as you're throwing darts, what I'm showing here is essentially how many accumulate in each of these vertices. And you see you basically get them all with roughly equal probability here. For this one, if you look at this for a second, you say, oh, you know, there's a little bit of difference, but there's these two here that essentially get almost, like you're very unlikely to get. So if you're throwing darts, it's going to take a while to get those. So what actually happens here? Again, this was another bit of fortuitous timing here. Around the same time we were working at this, we happened to have a conversation with some folks who had worked on a very similar problem from a different perspective, but essentially we were able to adapt their results and show that the probability that you get a vertex of the zonotope is proportional to the size of the normal cone of that vertex. And so what is the normal cone? If you've got a vertex, you sort of have this cone coming out at right angles. And so if you look at this and you say, hey, what happens as this thing gets flatter and flatter and flatter? Well, as it gets flatter and flatter and flatter, the size of that normal cone shrinks and shrinks and shrinks. So here's another zonotope over here. Here are all of the sort of vertices of the hypercube in circles, and then the x's are actually the vertices of the zonotope. We've drawn the regions here corresponding to basically the probability that you'll generate each of them. And you can see that there's these little slivers here where you're highly unlikely to get those vertices. Those ones correspond to basically flat sides of the zonotope. Okay, so this is zonotope sampling. Sorry, was there a question?
Was it just easier to draw them in a box instead of a ball or sphere?
Sorry,
It seems like in higher dimensions this is giving the wrong idea, right? Because the corners get bigger and so forth.
So I guess I have no intuition for higher dimensions. So yes, I guess in higher dimensions this is probably giving the wrong idea. But yes.
Is it coincidence that the ones that are unlikely to be sampled also have other vertices nearby?
So essentially that this one, this one here is unlikely to be sampled, but when you say vertices nearby.
That aren't part of the zonotope.
Oh,
So the 4 that are most unlikely.
that is a great question. The short answer is I don't know. I need to think about it a little bit more. So, okay, so back to correlation clustering. What the heck does correlation clustering have to do with zonotopes? Well, essentially, there's this thing called a signing zonotope, which allows you to associate vertices of the zonotope with clustering. So you specify the number of clusters you want. Turns out for low-rank correlation clustering, we know exactly how many clusters to expect. And then you generate a vertex of this, and then you sort of map those into a zonotope. So the vectors G here are given by your low-rank vectors times some information about R and S, where R and S represent clusters. And so these things are sort of confusing, but essentially what this means is if you get a vertex where this thing is -1, it means that node I is not in cluster R, but could be in cluster S. And so once you get one of these vertices, you have to sort of like back out what the actual clustering is by figuring out, oh, this one's not in cluster R, could be in S. Well, is it, just look at all S and things like that. And again, what this corresponds to is basically you do pairs of clusters because you're getting answers of the form not in R but could be in S. So there's some pairwise thing going on there. Suffice it to say, this isn't our stuff here. What we're doing is we're looking at this random sampling algorithm applied to these things. So again, rather than directly enumerate all the vertices of these things, which is going to be expensive and hard to do in practice, what we're going to do is just compute some large number of vertices via that sampling algorithm and find the clustering of each and just compute the objective function that we get. And so here's what happens as you vary the number of iterations from 1 to 20,000 in this case. This is a 3,000 dimensional problem that's 5-dimensional. So this would be like a 3,000 to the, 29 or something like that, or something 24. This is a synthetic problem here, but you can see that, again, we sort of get better and better and better, but just a little bit better on each iteration. So we start really good. The question is just really, can we explain this? And so if you want another cute example of this, so here is an instance of this where we took Google Trends data on how often people are searching for computer science conferences, and essentially detrended them and turned us into a low-rank correlation clustering. So now we're clustering conferences by how people search for them on Google. So this is over a few years. It turns out that there are essentially 2 clusters that come out of this. There are conferences whose search volume is decreasing and conferences whose search volume is increasing. I expect most people are publishing in these places and not in these ones, but we'd have to double check that. So curiously for this one, it's actually pretty easy to solve. So using our stuff, we can actually get an optimal objective value in about 7 seconds, I believe. So like the zonotope will find the correct answer pretty quickly. There's another common algorithm for correlation clustering called pivot. That one also finds it. It's even faster. This one's based on an LP that's extremely expensive to solve. It also finds the optimal solution, but it takes, a little bit less than an hour. You can also solve the integer LP for this one as well, which is how we know that these things are optimal. So back to the question, I guess for the purpose of these clusterings, are there better ways of sampling the vertices of the zonotope than just this simple idea that we've been looking at? But more importantly, is there anything like an approximation bound we can give for these style of algorithms based on some type of objective? And so if you want another reason why you might care about this, there's all sorts of nice relationships between solving low-rank binary QPs and Zonotope enumeration. So it'd be nice to sort of see what those are like. So again, just in summary, here are the two questions. So for the problem of Erdos-Renyi graphs, or those triangle Erdos-Renyi graphs, what the heck is this distribution? So hopefully I'll have an email off that might answer this one by the end of this. And then for this Zonotope sampling algorithm, what can we say anything beyond, yes, we get probabilities of those Zonotope, or sorry, we get vertices of those Zonotopes basically proportional to their normal cones. Thanks.
So we have time for questions.
Yeah.
So if we have a rank R positive definite correlation clustering problem, you said we know the number of clusters.
Yes. So we know the number of clusters. There's I think it's D+1 clusters. So this comes out of this vector partitioning problem. So it's easiest to see this in 3 dimensions. Actually, here, I can show it back here. So essentially, when you look at this like a vector partitioning problem, it turns out that in order to be optimal, the sum points have to be at larger than 90 degrees from each other. So in 2 dimensions, the number of vectors you can have at more than 90 degrees from each other is exactly 3. So for a rank 2 problem, you get 3 clusters. And it turns out if you generalize this, you get D+1 clusters. So that's the upper bound. You could have fewer than that. But in general, you're like, unless there's some further low dimensional structure or some sort of singular structure in these, you're not I mean, you'll use all of the clusters.
I had a question. If your algorithm was uniformly sampling points from the Zonotope, I know it's not, because if it was, does that give you something immediately for correlation clustering or for another problem, or it's not really clear? It's like there's 2 questions.
So there's 2 questions there. I mean, it's really like, is there anything? So at the moment, we don't essentially have a good map between anything about the objective function and vertices of these things, and so I don't even know if uniform sampling would help. There are other cases where that might actually help, but for this particular one, I don't think. The short answer is I don't know.
So if it's not a vertex, then you know that it's not related to an optical clustering.
Correct.
But that sort of suggests that if it's almost not a vertex, then it's probably not a very good clustering, right? So it sounds like there's some relationship between the normal cone probabilities and the possibility of it being a good clustering. Yeah.
Yes, I agree. That sounds reasonable. I'll Again, we'll need to do some more thinking about this. Yeah.
So if you do going back to your first part, you do this like triangle graph.
Yes.
And then what if you did that? If you did that with 4 cliques or 5 cliques or going on up, you get similar distributions, or you get?
We've looked at. I don't think I ever drew the eigenvalue plots for 4 cliques. The problem is that with Erdos-Renyi graphs, the probability that you get larger and larger cliques sort of decays quite rapidly. And so when we do social networks, yes, we do periodically look at 4 cliques and 5 cliques, and that's actually pretty interesting. But for Erdos-Renyi, I don't know that that's going to be all that interesting, just because at some point you're just
dense graphs.
Yeah.
Yeah, I see.
Yes.
So in your empirical results, do you think if the distribution depends on the choice of P as well, and you generate your Erdos-Renyi random graphs?
Oh, absolutely. So essentially what we're doing here is I'm varying average degree here instead of P, just because I can never reason about P, and I can always reason about an average degree. So essentially the probability P here is going to give, I mean, these are 3 different choices of P that are this one's quite more compact than this one is. This one actually is pretty interesting.
Okay.
Let's thank David again.
Thank you.